Hi, the section 7.4, the ordinal multinomial responses. So now we want to develop a regression model for an ordered response variable y, whose range is 1 to j. So we have order in these categories. So we just name it as 1 to j. And how to model? Okay, so we study at first the proportional odds model. The idea is to think about the probability of y's less than j. So not equal to, but less than j. So if j is 1, it's smallest, j is equal to capital J, it's largest, and j is equal to 2 or 4, it's in the middle. Then how to model this? We name this as gamma j. Then we assume that some g of gamma j, for example, the logistic function of gamma j, is equal to theta j minus beta transposed. So here theta j and beta are parameters, and x is predictor. So x is typically, okay, so p-dimensional. So beta is also p-dimensional. So transpose is the one times p. And this is additional parameter. And the point is that the beta does not depend on j. But here just constant does depends on j. So that's the difference. So basically the beta transposed x. So this part represents the tendency of y. So it's a kind of a good indicator for y. So for example, so the y have the economic condition. Maybe 1 is the recession and the 2 is the not working very well, and the 3 is maybe they're doing better, and the 4 is maybe the bubble or something. So then, for example, economic indicators, we have some general important variables such as unemployment rate or inflation rate. If we take a linear combination of those variables, then that is a good indicator. So that is beta transpose x. Then what is theta j? Theta j basically gives some threshold between those 4 categories. The threshold between 1 and 2, and 2 and 3, and 3 and 4. So overall, the beta transpose x dominates, I mean, controls the overall level of y, but the threshold is determined by theta j. So that is the idea. So in terms of space of predictor, so this assumes that so space of predictors, and suppose we want to predict the class, then proportional odds model idea is categories are predicted as this. So just the all parallel, but we have some threshold. And threshold, so the 3 tilted lines are determined by theta j. And the beta transposed x is the overall tendency. So this direction is defined by beta. So this is very restrictive in some sense. So in general, if we have x, the space of the predictors, you can arbitrarily divide to classify. For example, this is 1, and this is 2, and this is 3, and this is 4. But we cannot do this in this regression. Only we think about the case of this. Yeah, and this function g can be a different link function, such as probit or complementary log-log or Cauchy distribution, Cauchy function. Yeah, so this is the idea of the proportional odds model. And the y is the discrete variable, but the discrete variable is always hard to deal with. For example, we cannot think about the probability density function. So sometimes it's useful to think about the underlying function, underlying random variable z. So it's not necessarily normal, but the underlying, the continuous random variable z. We want to think about it. So the idea is that if y have several levels, okay, so suppose y has 4 levels and these are continuous, but suppose that we have the underlying variable z, and this corresponds to y1. So if the z falls in this area, then it corresponds to y is equal to 1. In this area, y is equal to 2 and 3 and 4. So in this way, we can transform this discrete random variable y into continuous random variable z. And how to transform y to z? At first, we defined the proportional odds model. So that is the log of gamma j over 1 minus gamma j is equal to the beta x, the theta j minus the beta transpose x. So if we put the inverse function on both sides, then the gamma j is basically the inverse logit function of theta j minus the beta transpose x. But so this z, so z beta transposed x follows a logistic distribution, this function, then z minus beta transposed x is less than theta j minus beta transposed x. So this probability is this by the definition of f. So, and actually the right-hand side is the same as the previous equation. So that means the gamma j, that is probability of y is equal, less than or equal to j, that is actually equal to this quantity. And you can see that the negative beta transposed j is common. So we can write this as probability of z is less than theta j. So in this way, the gamma j is characterized as the probability of z is less than theta j. So, or in other words, the probability of y is equal to j is equal to probability of z's between theta j minus 1 and theta j. So in this way, that we can generate a random variable z, which represents the discrete random variable y. And lastly, I would explain the proportional odds model. Probably the more appropriate, name is maybe ordinal logistic model or something like that. But we say proportional odds model, and here is the reason. So if we think about odds is the proportion of the some probability and 1 minus that probability. But if we have the two different data points, then we can compare these two odds. Then these two odds have relatively simple shape because originally this is exponential of negative the beta transpose x1, but if we take the difference between the two terms, the one for x1 and the other for x2, then we can combine this because this is exponential function. Right, so this term and this term, then the division, so the ratio is just the subtraction in exponential function. So that's why it's called the proportional odds model. So basically, the difference between odds is proportional to the difference between x1 and x2. Yeah. So so this is the theory for the proportional odds model. Okay, so now that we have just one a kind of the theoretical thought, and how many parameters are there in the log odds? Sorry, how many parameters in the proportional odds model? Then actually the number of parameters is much less than the multinomial logistic regression. And because, okay, so suppose we have the 10 levels of y, then just one predictor. And what happens? This, the proportional odds model. So this explains the probability of the y is equal to 1, or y is less than or equal to 1, is represented as the theta 1 minus the beta x. So probability of, maybe we have to change the by the log scale and actually the logit function. But anyway, so this is less than 1 and less than 2. And up to less than 9, because we have 10 categories. So y is less than 10. That is trivial. So that probability is 1. So we have the 9 different terms. But we only have one beta. I write beta 1 because it's the coefficient of the first predictor x. And then we have the theta 1 to theta 9. So in total, we have only 10 parameters. But in multinomial logistic regression, so these parameters are just the choice. So we have the 9 by 2, so we have 18 parameters. So multinomial distribution does not assume relationship between categories. So we have to have more flexible model, but the ordinal model, we have stronger assumption and we have smaller number of parameters. So it's more efficient to present the relationship between x and y.